Welcome to Abigail's Math Vlog. Today we are covering Green's theorem. Green's theorem is another higher dimensional analog of the fundamental theorem of calculus. It relates the line integral of a vector field around a plane curve to a double integral to the derivative of the vector field in the interior of the curve. Green's theorem gives the relationship between a line integral and a simple closed curve C and the double integral over the plane region D, bounded by C, and can be written in three ways: normal form, flux form, and circulation form. Let's start with an example. We have a two-dimensional XY plane. We have our region D bounded by four line segments. We can call this C1, C2, C3, and C4. The relationship between the line integral and around the simple closed curve C and the double integral over the plane region D, which is bounded by C. Green's theorem is named after George Green. It's a two-dimensional special case of the more general Kelvin-Stokes theorem, regarded as a direct application of the fundamental theorem. George Green, born in 1793, was a British mathematical physicist who wrote an essay on the application of mathematical analysis to the theories of electricity and magnetism. His essay introduced several important concepts, among them a theory similar to the modern Green's theorem, the idea of potential functions as currently used in physics, and the concept of what we now call Green's function. Green was the first person to create a mathematical theory of electricity and magnetism, and his theory formed the foundation for the work of other scientists such as James Clerk Maxwell. His work on the potential theory ran parallel to that of Carl Gauss. Green's life story was remarkable in that he was almost entirely self-taught. He received only about 1 year of formal schooling as a child, between the ages of 8 and 9. Before stating the Green's theorem, we need to understand a few topological ideas: simple connected regions and orientation. First, let's consider a closed curve C in a two-dimensional region, parametrically by r to t equals xt plus yt, with a being less than or equal to t, which is less than or equal to b. We can say that C is a simple if it does not intersect itself. A region is called simply connected if the boundary is simply closed curve. So let's look at this. A simple connected curve, or considered something like a circle, looks as such. Or is this shape. These are two examples of simply connected. A curve intersects itself if RU equals RV for two distinct values U and V. A circle is a simple curve, while a figure eight is not simple. So our not simple curves where RU equals RV, or a figure eight. As we see, it intersects itself and is no longer a simply connected curve. Lastly, orientation. If we traverse a curve in the opposite direction, then the line integral will be negative of the origin. Therefore, a positive orientation can be defined as: let R be a simply connected region. We have a simply connected region that doesn't intersect itself with boundary curve C. Then C is called positively oriented if facing the direction that the curve is sketched. The region lies to the left of the curve. So as we sketch the curve, this would be positively oriented as long as our region is to the left when we sketch. If we sketch and it's to the right, then this is a negatively oriented region. Now that we have covered the topology, let's get into Green's theorem. Let R be a simply connected region. So we have a simply connected region with a smooth boundary C. So our boundary C, positively oriented. Therefore, when we sketch, everything will be to the left. As we go around our boundary C, we have it positively oriented. And let M and N have a continuous partial derivative in an open region containing R. Now let's look at the function. We have the integral of M dx plus N dy, which equals the double derivative of the region partial N over X minus partial M over Y. So dx dy. We can assume that the region is both vertically and horizontally simple. Otherwise, we can carefully cut the region into parts so that each of the parts are both vertically simple and horizontally simple. So here, we could, if this wasn't simple, we would be able to cut this to where it was both vertically simple and horizontally simple. Notice that the lines where the regions cut downward once and upward. So here, cuts are downward, and here, cuts are upward. So the cuts drawn once downward and once upward. Thus the two line integrals over this line will cancel each other out. We will show the regions sufficiently simple shapes in the proof. We'll start with proof 1. We'll start with the integral of M dx. And this is still equal to a double integral for the region. And it's going to be partial M over Y dx dy. Then we'll move on to our region N. So again, we have our integral N dy, which is equal to the double integral of the region partial N over X dx dy. And the sum of both of the integrals equals 1, completing our proof. Then we can move to the second proof. So let's start off with our boundary on our two-dimensional xy plane. So with our figure 1, we'll have our first line A, second line B, and then we're going to start with a simply connected region. So this will be our simply connected region, and we want to ensure that it's positively oriented. Therefore, our orientation marks, as they trace our region, the region will be to the left. So now we have the boundary of region R, which consists of the lower region curve y equals y1, x, and the upper curve y equals y2x, as in figure 1 that we see here. Let C1 and C2 denote the lower and upper regions of the curve. So again, for our upper portion, we have y 2x, and for the lower portion we have y equals y1x. Now that we have traced our function, let's start with the second part of our proof for m. For m we have the integral of all of m dx, which is going to be equal to part 1 and part 2 of m. So this will be equal to c1 of m dx plus c2 of m dx. Now let's look at the line integral just for c1. For c1 we have the integral c1 of m x y dx, which is equal to the integral with the upper region d, lower region c, m x y1 x dx. And then for the line integral for c2 we have, for c2, we have an integral of m x y dx, same as the beginning, which equals the integral with upper limit d, lower limit c, m x y2 x dx. And this is going to equal the negative integral with upper region d, lower c, m x y2 x dx. Thus, what all of this says, if I can get this to erase, is that our integral for c, m dx, is equal to the negative integral with upper limit d, lower limit c, m x y2 minus m x y1 dx. Now let's consider the double integral for the region M. So we have the double integral for the region of partial M over our partial y dx dy, which equals to the integral with the upper boundary of d and the lower c, and the second integral of the upper y2 with the lower y1. And this is for the partial m over partial y dy dx. We can use the fundamental theorem of calculus in order to calculate this. I'm going to go ahead and get rid of our graph above. So when we use the fundamental theorem of calculus, we have the integral for y2 for upper and y1 for lower for the partial m over partial y dy, which is equal to x mx y2 minus m x y1. So then we'll take that with a double integral for the region partial m over partial y dx dy, which is equal to our integral with upper D, lower c of mx y2 minus our mx y1 dx. Therefore, that gives us our double integral, our integral for the region C, m dx, gives us a negative double integral for the region R of partial m over y dx dy. So once we've completed this portion, we can move on to our second portion, which was n. When writing the function for n, we still have the integral for c of n dy which equals our double integral for our region, as we have here, for the partial n over partial x dx dy. And we can evaluate n in a similar way that we did in for m, adding the two sections together. For more complicated shapes, which would cause more complicated functions, we can break the function in two, or we can break the shape in two to give us two completely different functions. So if we had a more complicated, simply connected, positively oriented region such as this, we could break it in half here, ensuring that one line goes up, the second one goes down, which gives us one positive integral and one negative integral, which will cancel each other out. Green's theorem can be used on complicated shapes. We just divide into our simple regions, and each integral corresponding to them can divide in each equation, but ensuring that we have opposite orientation canceling each other. Let's start with an example. We're going to start with a positively oriented, simply connected region on a 2D plane. So we have our 2D plane, x and y, with our simply connected region. So we have our region, positively oriented, so as we trace our region, the region will always maintain to the left. And our function is going to equal y equals 2x. So for this, our function is going to be the integral on a closed boundary, C, we'll have x squared minus y squared. That's going to be dx plus 2xy dy. So as we note, we can take our double integral for the region. So we have our double integral of partial m over partial x minus partial n over partial y. So our partial m over x minus our partial n over partial y dx dy. So the curve on the boundary for our region R, x, y, so we have R, x, y. Our x is going to be, 0 is going to be less than or equal to our x, which is going to be less than or equal to 1. So 0 is less than or equal to x, which is less than or equal to 1. So we have our region xy, where 0 is less than or equal to x, and x is less than or equal to 1. And then for y, we have 2x squared, which is less than or equal to y, which is less than or equal to 2x. So 2x squared, which is less than or equal to y, which is less than or equal to 2x. So for our equation, we'll have the integral with our double integral with our upper region of 1 and our lower boundary of 0. And then we'll have our second integral with our upper region y equals 2x and our lower region where y equals 2x squared. And this is with the function of 4y dy dx. So I'm going to erase this so we can start working this problem. So again, I'm going to rewrite our equation. We have the integral of our simply connected region, x squared minus y squared dx plus 2xy dy. Integral with the upper at 1 and the lower at 0, and the second integral with the upper y equals 2x and the lower y equals 2x squared for 4y dy dx. When we calculate this, we get the integral 1 to 0 of our 2y squared and again we're taking this to y equals 2x for our upper and our lower y equals 2x squared for dx, and this will give us 8x squared minus 8x to the 4th power dx. When we integrate this function, we're going to get 8 over 3 x cubed minus 8 over 5 x to the 5th power. And again, we're taking that with the upper boundary of 1 and the lower of 0. So that's going to give us 8 over 3 minus 8 over 5 minus 0, which equals 16 over 15. So the second form of Green's theorem that we're going to talk about which references Gauss's theorem in circulation. This form of the theorem calculates the circulation around a boundary and sets it equal to the total circulation inside of the boundary. The total circulation around the boundary equals to a curl times the area, where the curl circulation per unit area. The theorem for the circulation curl form states, let C be the piecewise smooth, again simple closed curve, enclosing a region R in the plane. So now let's look at this. Let our function f equal mi, as this is going to be a vector, plus n j, which is a vector filled with m and m having the continuous first partial derivative in an open region containing r. Then the counterclockwise circulation f around C equals the double integral of the curl f times k over the R region. So we're going to let R be the region in the plane with the boundary curve C. So here we're going to have f, which is going to be p, q, which is a vector field defined on R. Then the new formula is going to be the double integral for our region, and then we're going to have the partial n, which is going to be over x, minus partial m, which is going to be over y. Then we're going to have, that's going to be to dx dy. For up here, this should actually be f is equal to m n instead of pq. So once we have that, that's going to equate to our single integral f, and we're going to multiply that to t ds. Now we can use this to represent the circulation of f around C. If we were to take the velocity field of water flow of a fluid per unit area per unit time, the integral would indicate how much the water tends to circulate around the path in the direction of this orientation. For Green's theorem for circulation can be applied if a floating paddle was spinning in water. So if the paddle is spinning, then we can calculate the circulation from the boundary as it's spinning around the axis located in different points. One can imagine that a lot of tiny circulation is a bunch of closed curves inside of the larger one. So we can see all the smaller circulations as the paddle is spinning, causing smaller circulations here to ripple out. Green's theorem is simply the relationship between the macroscopic, right here, circulation around the ends of the paddle and the sum of either the microscopic circulations here at any given point along the paddle. Green's theorem has been an instrumental part of physics with the use of electric flux, electric charge on a surface, electric fields, Gauss's law, force of pressure, and others on areas of mass and flow. The equation for flux form is the same as the equation for circulation. We have a two-dimensional function around a closed contouring using Green's theorem to find the area enclosed by the two-dimensional curve or the velocity field of the flow, as well as other engineering applications. Green's theorem for flux divergence form states, let C be a piecewise smooth, simple closed curve enclosing the region R in the plane. So again, we're going to have F equals Ni plus Mj, as again this is going to be another vector field with m and m being continuous first partial derivatives in an open region containing R. Then the outward flux of F across C equals the double integral of F over the region R enclosed by C. Therefore, we have our double integral for our region the divisor F for dx dy. And this is going to simply equal our single integral for C, and then flux, we're going to multiply that by the n ds. This formula will be used to find the flow rates or a flux of a fluid flowing into a plane or across a rectangular boundary. The rate at which the fluid leaves the boundary is going to be our F at xy, which would be equal to our n xy I plus m xy j. The formula gives the scalar component of the velocity such that if the flow is measured in meters per second, it would be multiplied with meters or squared meters per second. The net flow can be calculated by adding up the top, bottom, right, and left edges using the dot product. In order to do this, we have to add the opposite pairs to get the top and bottom of the formula. So we're going to have n xy plus, we're going to need the change in y. And then we're going to subtract this from n xy, and we're going to multiply that by our change in x. And then for the right and left sides, we're going to take our m and x plus the change in x, y. So we have our m, x plus the change in x, y. And then we're going to subtract that from m, xy, which is going to be multiplied with the change of y. So once we put this together, and for the top we'll get, we're going to look at f's going to be x of y plus change of y, which is going to be multiplied with j, which is change of x. And then that's going to equal a negative n xy plus our change of y multiplied with change of x. Then whenever we look at the bottom, this is what we're going to use for the bottom. We'll have our f xy, and we're going to multiply that with our negative j change of y. Actually, we'll multiply that with change of x. And this will equal negative n xy change of x. So the right formula will be, here we had top, bottom, and then right. So the right formula is going to be f x plus change of xy and it's going to be multiplied with I change of y. And that's going to equal mx plus change of x multiplied with change of y. So now the only thing we're missing is our left side. So left is going to be similar. Again, we're going to have our f, x of y, x and y. And we're going to multiply that with negative I change of y, which as you see is just the opposite here. And that's going to equal our negative mxy multiplied with our change of y. Then we can add the opposite pairs to get the top and bottom formulas. So this is going to equate to n for xy plus change of y minus our nxy multiplied with our change of x and for the right and left side we're going to have mx plus change of xy and that's going to be subtracted with mxy multiplied with change of y. So as we've gone over today, Green's theorem gives a relationship between a line integral around a simply closed curve C and a double integral cover the plane region D bounded by C. Orientation has to be simply closed curve and it must be positive. Green's theorem can be used in regions that are not only simply connected by breaking them up into numbers of simple curves. Thank you for watching this presentation.